Hello and welcome to this video about matrix proofs. In this video we'll prove that the row equivalence relation is an equivalence relation. They must have proved that it's an equivalence relation first before they called it row equivalence. So now to define what row equivalence is. It's when there is a series of row operation matrices that can be multiplied on the left by one matrix to transform it into another matrix. It turns out that applying a series of row operations to a matrix that can transform one matrix into another also makes these matrices row equivalent. But that's really a consequence of the first main definition, because performing a row operation on a matrix is the same thing as multiplying a matrix by a row operation on the left. So I'll just write this down using mathematical symbols. The capital letter E can stand for a row operation matrix. We'll use this squiggly line to stand for row equivalence, since that's what's normally used. It also stands for similarity, which is different, so we'll define it when we use it. In order to show that a relation is an equivalence relation, it's necessary to show that it satisfies these three conditions. That it's reflexive, that is, a matrix is always equivalent to itself. That it's symmetric, that if a matrix is equivalent to a second matrix, then the second matrix is equivalent to the first. And finally, that it's transitive, that is, that if the first matrix is equivalent to a second and the second to a third, then the first must be equivalent to the third. So now to prove the first property, that any matrix is row equivalent to itself. Most people would say that's obvious, but I think that it can be proven properly. We'll use the fact that any row swap operation is its own inverse. And we can use the row swap operation that swaps the first two rows in a matrix. This is ideal because it can be used on a matrix with any dimensions, except for matrices with only one element, which can be ignored for the moment because they're effectively scalars. We'll define this matrix to be the row swap matrix that swaps the first two rows. Now if we multiply matrix A by this string of row operation matrices, then they'll multiply together to become the identity matrix. We can multiply them together first before multiplying A because of associativity. And I multiplies by A to give A, which is a consequence of theorem 1.4. So this series of row operation matrices multiply on the left of A to give A. So A is row equivalent to itself. Let's just have a closer look at a row swap matrix. Here's an example of a 5x5 row swap matrix. I thought I need to give a more concrete example. This matrix swaps the third and fifth rows of a matrix, and it can multiply by itself to give the identity matrix. And here's an example of it doing this. Now to show that this relation is symmetric, we have to show that every row operation matrix has an inverse. So we've seen before that row swap matrices are their own inverses. They'll just swap the same rows back again to their original places. We have to show that row mole matrices have inverses. For example, we could have a row mole matrix that multiplies a row by a constant C. Then there's another matrix that divides this row by C again, so that's the inverse of this row mole matrix. But this would be the row mole matrix that multiplies a row by the reciprocal of C, so it's a row mole matrix too. So let's have a look at an example of a row mole operation matrix. It's an identity matrix with one entry in the diagonal that's not equal to 1 or 0. Here's a row mole matrix that multiplies the second row by 7. And here's its inverse. It multiplies the row by 1 over 7. It divides row 2 by 7 and should reverse what's done on it by the first matrix. So let's try multiplying them together. So the entry where the non-1, 0 entry in the matrix is located undergoes this multiplication of 1 over 7 by 7 to get 1 in this location, which gives us the identity matrix. So this is the inverse of the row mole matrix, and it's also a row mole matrix itself. So the inverse of the row mole matrix is also a row operation matrix. The row add matrices have inverses too. Like for example, this is a row add function. It adds C times the second row to the first. And this would be the reverse operation, to subtract C times a second row from the first. So this is an example of a row add matrix. It looks like an identity with an extra non-zero entry in the non-diagonal region. In this case it's 11. We're adding 11 times a particular row to another row. And this is its inverse, just getting the negative of this number in this location so as to subtract 11 times a row from another row. So let's try to multiply them together so as to get the identity matrix. So this is what happens at this location. We get this expression which needs to be evaluated. And evaluating it gives us 0, so that we get the identity matrix. And so these are all the cases of row operation matrices. So every row operation has an inverse. And every inverse of a row operation matrix is itself a row operation matrix. So I'll move things up and off the screen to make more room. So then if A is row equivalent to B, then there is a sequence of row operation matrices that multiply by A to give B. So then there are another sequence of the inverse of these matrices that multiply B to give A, and these matrices are themselves row operation matrices. So we can say that B is row equivalent to A in this reverse order. So now we've proven that this relation is symmetric. So now to prove transitivity for this relation, that's written here. So now to prove it, we'll use the definition to describe B in terms of A. And similarly, we'll describe C in terms of B. So we can combine these two equations to get a list of row operation matrices that can describe C in terms of A. It's just the two lists of row operation matrices combined together. So we can multiply matrix A on the left by a series of row operation matrices so as to get matrix C. So this is the definition of row equivalence, so that A is row equivalent to C. And so this proves that this relation is transitive, and so we've proven that row equivalence is an equivalence relation because it's reflexive, symmetric and transitive. And we've thus completed the proof and can draw the customary black square to mark the end of this proof. So I hope that you found this video to be helpful and educational. Please click like and subscribe if you did. Feel free to post up any comments and to share this video, and thanks a lot for watching.